Section 2.8 is automorphisms of a group. So we will have the sections content in the form of section A, section B, section C questions. First one is define an automorphism of a group G. Second one is define, this is section A question. Define the inner automorphism corresponding to an element G in G and write down script A of G for all cyclic groups. Then in section B, we can have prove that the set of automorphisms of a group G is a group. And second, we can have prove that the set of inner automorphisms of a group G is a normal subgroup of the group of automorphisms of G. Third, we can have in section B, if G is a group and phi an automorphism of G, and if A belongs to G is of order of A, then order of the image is same as order of the element. And we can expect this question in section C, that prove that G by Z is isomorphic to, rather here you should have I of G is isomorphic to, I of G is isomorphic to G mod Z, where Z is, this is here isomorphic. Script I of G is isomorphic to G mod Z, where script I of G is the group of inner automorphisms of G and Z is the center of G. See, for the first question, the answer, that is define an automorphism of a group G. If we have phi to be a mapping from G to G, which is one-to-one onto homomorphism, then we call this phi to be an automorphism of G. So if G is the given group, then if we give the definition this way, then we have that phi to be an automorphism of G. Next is the definition of inner automorphism corresponding to an element G of G. We'll consider G to be a group and small g to be a member of capital G. We define this mapping T suffix G from G to G by it takes any element x to G inverse xg for every x in G. Then this Tg, you can easily prove that to be one-to-one, onto and homomorphism. See, for one-to-one, we consider it is defined. If you are given such a mapping, then there is no need to check the well-defined part. But if we are defining means, then we'll have to check the well-defined part. So we'll consider x to be equal to some y. Then pre-multiplying by G inverse and post-multiplying by G, both sides, this is what we get, G inverse YG. So this is nothing but the image of x under Tg, and this is nothing but the image of y under Tg. So this shows that your Tg is well defined. This is for well definedness. Then for one-to-one, just to retrace the steps, we have to assume the images to be equal. So that in turn gives this. So here by LCL and RCL, you have x to be equal to y, the pre-images to be equal. So we have both well-defined and one-to-one from here. And to prove that Tg is onto, we'll consider y in the codomain G. See here, both domain and codomain are G. We shall mention that y belonging to G, which G that we consider, the codomain G. Then by considering, see, we need to find the pre-image for that, right? So if we consider G, Y, G inverse, this one will act as the pre-image, and this is present in the domain because G is present, Y is present. So this is present in this domain G. This belongs to G, which here it denotes the domain. Now to check whether what we have written is right or not, we shall consider G, Y, G inverse under Tg. So it will be G inverse G, Y, G inverse G. So this and this being identity, we get just y. So where we started with y and we have landed up in y. So that means for y, G inverse is the pre-made, therefore the function is onto. Already we have shown that it's well defined and one-to-one. For homomorphism, we will prove like this. We'll consider two elements, say x and y, xy, tg. So this will be G inverse x, y, g. We can introduce here G inverse, so that after associativity, using associativity, we can have this to be x. This one is nothing but the image of x under tg. This one will be the image of y under tg. So we have this tg to be homomorphism also. So this is our inner automorphism, this tg, which is defined in this way. We are asked to only define the inner automorphism, but if you are given this and asked to prove that this is one-to-one onto homomorphism, then this is how it should be done. So TG is one-to-one onto homomorphism and is called inner automorphism corresponding to G. Now the next one is a random script A of G for all cyclic groups. We'll consider G to be finite cyclic group first. G is generated by A and order of G is n, say. Then script A of G is given by, it's a result, it's only the statement of the result that we are giving. It's asked in section A. So it is all those elements of this form T suffix T with T less than n and T and n are relatively prime. So n is the order of G and this T is in the suffix that we denote. So this is a number. It is see, in the case of inner automorphism, we had this TG, there G is a member, but here it is not that, it is a number which is less than n and relatively prime to n. Now this TT, how it is defined from G to G, it takes the once how generator is taken, any element's image can be easily known. So A under T suffix T is nothing but A raised to T, and this tell us that, say for example, if we have G to be say 1 minus 1 I minus I, it's a finite cyclic group, order of G is 4, and so in the case of Klein's 4 group, here we consider n to be 4. So the numbers which are less than 4 and relatively prime to 4 are 1 and 3. So that means T1 and T3 will be members of our script A of G. Where how this T1 is defined, it takes the generator I to, this generator will be taken to I power 1, and you have the generator I, another mapping being taken to I cube, that is minus I. So this is what this is how we have our T1 and T3 being defined. So we'll have to mention what the script A of G is first, and then the elements, how are they defined. This is how they are defined. So this is enough to remember, so that whatever may be the finite cyclic group, we can easily write out the suffix 1, 3, 5, 7, whatever it is, we can easily write out. The next one is G is infinite cyclic group, means we have only two automorphisms, one is T1 and the other one is T suffix minus 1. So T suffix 1 will take the generator A to itself, and T suffix minus 1, that mapping takes any generator A to its inverse. So that is how script A of G is defined, the case of infinite cyclic group here and finite cyclic group. Right. Then section B, prove that the set of automorphisms of a group G is a group. Now we'll consider G to be a group and A of G to be collection of all bijective functions on G. See what we have what we had already is if G is a group, then A of G denotes the set of all bijective mappings from G to itself, and this contains script A of G, which is here 1-to-1 onto alone, here 1-to-1 onto an homomorphism, and this one contains script I of G. So this one is special type of automorphism. That is, it takes Tg, which takes x to G inverse xg. So it is special type. So the bigger one is A of G, and in that you have script A of G, and within that only you have script I of G. So here we are asked to prove that script A of G is group. So we are going to establish this by showing that A of G, in A of G, this one exists as a subgroup. So A of G is a collection of all bijective functions on G. Then script A of G is a subset of A of G. That's very obvious. Then since identity element is 1-to-1 onto and homomorphism, script A of G must contain that, and therefore it is non-empty. Now we'll consider two elements in script A of G. Then both T1 and T2 are 1-to-1 onto and homomorphism. Because it is in script A of G, so we have bijective homomorphism from G to itself. Remember this again, this T1 and T2 doesn't play any role of T1 and T2, which we mentioned in the previous problem. That is different, this is different. So now T1, thus both T1 and T2 being members of this are 1-to-1 onto homomorphism from G to itself. Now composition of bijective mapping or composition of homomorphism is again a homomorphism, and similarly inverse of bijective mapping is bijective, and inverse of a mapping which is of course 1-to-1 onto homomorphism, we have that to be also to be a homomorphism. So these are referred from section 2.7 where in one of the results that we have established that isomorphic 2 is an equivalence relation. So that result is recalled here. We haven't actually proved anything here. So just borrowed that result. So we have this T inverse is also bijective. It is already proved in section 2.7. T inverse is also a homomorphism. Therefore, T inverse is a member of script A of G. So a script A of G is a subgroup of A of G, and so it's a group under composition.